Hi, my name is Lakshya Jain, and today I'm going to be talking about my thesis, which is Discover, Intervene, and Adapt. This is about our reinforcement learning agents that learn causal structure, they treat skills as interventions, and adapt for generalization and interpretability. So I'll show you what the method looks like, what my observations were according to the evidence. And let's start with our outline for today's talk. So I'll start with a motivation, introduction, some background and methodology, and then move to results and conclusions that we got from this thesis experiment. All right, so let's define what the problem is. So the problem with reinforcement learning um, is that it learns a policy for actions over states, and that it does by trial and error, and it learns to maximize the cumulative reward using this policy. um, so the problem is that given actions given states means that it is uh, overfitting to correlations, which means that if you change the data distribution that this was trained on, and you try to test it on a different distribution, you will get very poor results because there's no policy available for the new state space that was introduced. So that means that it is overfitting to the correlations of the world instead of learning mechanisms of the world. Also, this is brittle, as we said, as soon as you change the distribution, it breaks, um, and it has opaque behavior. So it's pretty hard to know what's going on with the behavior of the agent or the thinking process of the agent, because this is all done using a policy and a random reward, randomized trial and error based reward learning. So overall, like traditional reinforcement learning agents, they fail pretty bad whenever you change the distribution you're testing it on. If you haven't trained on that distribution, so this is a paper from OpenAI where they were testing generalization performance for traditional RL agents. So the generalization performance was measured over 500 different levels in each of these different Atari game environments, and the train and test distributions are shown. So the train in blue looks pretty good, but whenever you go into testing one of these agents in a similar environment in which it was trained on, but there's a different distribution, it just fails. It just can't generalize. So most of them have a very bad performance on generalization type tasks. So let's look at the landscape, um, and the gaps that are there in research where people have tried to bridge this problem's gap. So there's one side of causality. So causality gives us structural causal models. It gives us two calculus and discovery, causal discovery, where we are exploring this causal structure of the world and how things are connected to each other. That We have learning algorithms for those, like a PC algorithm and the no tiers algorithm. We also have early formulations for causal RL, which were developed by Elias Barenboim, which I'll be talking about further. But all of these, generally, they consider us having expert knowledge of some aspect of the environment that we are exploring. Either we know all the interventions that we can perform, or we know all the also causal variables that we need to observe. That that would probably not be the case where we are trying to learn about an environment from scratch and then use that information to solve the problem, which RL is trying to do. So there is a gap there. So also a lot of this analysis was done using fixed graphs, and it doesn't do online um, learning with its own interventions. So I want to bridge the gap between causality and RL a little bit. I want to learn when and where to intervene, along with the causal graph itself, which will help us learn the causal graph better. Then, alongside that, we have a hierarchical array where we have frameworks like options and soft options critic. These they discover skills, uh, which are reusable, composable skills, but without having any explicit causal semantics to it. So these skills, they know how to execute some skills, but they don't know what these skills are changing in the environment and how it's going to lead you to the goal. So that's the second side. The third side I've explored is exploration, which is based on intrinsic motivation. So this was recently done using causal curiosity, which was a ICML paper where they did self-supervised experimentation. Uh, that approach does encourage exploration, but it explores without having a mechanism grounded planning layer. So that's where my work comes in. I'm trying to unite all three of these. I'm trying to discover structure using the agent's own intrinsic motivation and uh, information gain. I'm trying to intervene with skills I learned and then adapt my policy according to these two steps. So that's where I am trying to do. That's what I'm trying to do. So let's uh, go to my research questions. So I have three research questions which I defined. One is discovery. So, can the agent learn a causal graph on its own interventions and use it to plan and adapt? Uh, Second question is about interventions and exploration. So, do skills as interventions, do they, along with information gain, do they yield reliable subgoals and sample efficiency? The third question is does this generalize under a distributional shift and remain interpretable? Um, so we'll go through these questions later on as well. Uh, so my hypothesis is that if the agent maintains a probabilistic causal graph and reduces it, its uncertainty, then if it treats skills as subgoal targeting interventions and it intervenes discovery with adaptation, then it achieves reusable, composable control with better generalization, along with sample efficiency and interpretability compared to pure reward maximization. So from moving from reward chasing to causal reasoning, we have a causal RL framework that was introduced by Alas Barenbaum. So this describes the environment as a structural causal model, where the structural causal model is an abstraction on top of the environment. So the agent can't directly look at the structural causal model, but it can see the environment and observe and change things in the environment. So the agent on itself, it maintains a causal diagram, which is a subset of the structural causal model. A structural causal model is a model that defines all of the causal links in the environment, and a causal diagram is a subset of that the agent knows about. So that's the agent's belief space. So let's go to what interventions and do operator means. So in this example, we have age that affects treatment, and we have age that affects health. We also have treatment that affects health. So we'll define what an intervention is. So intervention involves actively changing a variable to observe the effect of that variable's change. So we'll set, in this example, we'll set the treatment variable to 1. So now the patient is being treated, and we want to measure the effects of what treatment does to their health. So when we do this, we change the value of treatment to 1. And when we change the value of treatment to 1 artificially, that means that it's no longer taking input from the age. So age is no longer affecting treatment in this situation where we turn on the treatment. So we have a mutated causal graph, and now we can isolate the effect of treatment and measure it. The do operator is a notation to denote the do operations, which are interventions. So P of y given do x means the probability of y when we intervene and set the value of x to a specific value. So now let's go to our proposed architecture. Right? So here's DIA, where there are three parts to it: discover, intervene, and adapt. So the way it works is we have observations as input from the environment, and we have encoders that take in that information and turn it into xt, which is an environment variable. uh, so we take the structured information, so we take this abstraction that we can take as input, symbolic information as input to our two graphs, which are probabilistic causal graph and skill intervention graph. We will be learning the structure for both of these graphs with algorithms. So the probabilistic causal graph contains causal beliefs, which are q phi a, and they have edge posteriors pe, and this is a directed acyclic graph. Uh, then SIG is skills or options with policy pi, terminations beta, and prerequisites I. Right. So next we have decision modules, which are a planner and intervention selector that choose novel, confirmatory, or goal-based interventions, and they use an information gain term to decide which one to be used, and then they implement the execution, and we track the sub goals. And then how the loop goes is we discover first, and then we reduce the uh, entropy of the graph, and then we adapt uh, by optimizing extrinsic reward, and then we execute the do intervention, and then we track sub goals, uh, which are xi comma f in the environment variable goal space, and then we update all of our parameters accordingly. Right. Let's go to an example. So we have this Minecraft 2D Minecraft world where we have a rich hierarchy. In this example, in the small example, I'll take the goal to be get some coal in your inventory. Right? So at the start, my agent has no information, so it is going to want to do some random intervention, which gives it some information about the world, and it tells you which interventions are valid right now. Okay. So we first go to this diamond and try to collect the diamond. In this case, the agent is not able to collect the diamond because to collect the diamond, you need at least a good pickaxe, like iron pickaxe, right? So that's a sub goal that is in later on in the hierarchy. We haven't reached there yet, so we can't explore that. So we'll explore something else. So we'll go to the tree and get wood from the tree. So in Minecraft, as we know, we can get wood from the tree without having any tools, right? So we will take wood from the tree and we'll put that in our probabilistic causal graph that you can get wood from a tree. So wood is a variable that listens to tree, right? And then we also did an intervention here which changed the value of a environment variable, so we can note that down as we modified something in the tree, which is chop tree, right? And then in this way we have achieved a sub goal called acquire wood. So our sub goal is also complete, acquire wood. So in this case, we have a probabilistic causal graph learning, right? So the learning objective for PCG, so we learn a structure and conditionals jointly. So the objective function is there, second line on your screen, where uh, we have this one whole likelihood term which talks about fitting interventional outcomes into uh, candidate directed acyclic graphs. So that whole term is doing that. Then we have another term to reduce the number of edges and to increase the sparsity, because we want the simplest explanations. We don't want extra edges that are unnecessary. Then we are also looking for acyclicity because we're running directed acyclic graphs. So we impose a penalty for breaking that condition. And then we want to regularize to simple priors. Um, so we put that KL term there. So that is for regularization or calibration. So and then we parameterize the Q phi and P theta and optimize both of them together. And that result is a calibrated posterior whose entropy drops as you keep getting evidence. Okay, so let's keep moving with our example. So now that we got the wood, now we can craft a wooden pickaxe. So there is a precondition there for crafting a wooden pickaxe that you need to be on the crafting table. So the precondition is captured. So now we are capturing an option. So there is a precondition that you need to be on the crafting table, like there was a precondition for tree to be on the tree, right? So we have to get our agent to the starting point for to activate that skill. Then inside the skill there are some moves to be done, like place all the wood on the crafting table. That's a intra policy for the activity of crafting table, the option. And then there is an end condition where you once you get a wooden pickaxe in your inventory, you can stop the activity, right? Okay, so this is how we express those things as skills. So we have the initial predicate, which is a precondition. We have intra option policy, which is the primitive actions until the option ends, and then the termination rule is when the option is going to end. We also keep track of sub goal, where sub goal is GK, where that's the goal we're trying to achieve. Xi is the environment variable which we care about in this particular sub goal. So that might be turning the number of pickaxes to one as a sub goal. And then we have predicates on Xi, which are stored in F, which is uh, evaluated on transitions, and it returns 0 and 1. Okay, so now that we have a wooden pickaxe, now we can craft a stone pickaxe. For that we need stone. Now we can mine stone using the wooden pickaxe. So we go and mine stone and we collect some more wood using the intervention that we already know. And once we have both of those things, now we can go back to our crafting table. So we have acquired stone in the sub goal, and then we go back to our crafting table with the wood and the stone, and we craft a stone pickaxe. So stone pickaxe is now acquired, and that's the sub goal that we completed, and we updated our PCG and SIGs accordingly. Okay, and once we have the wooden pickaxe, now we just have to go and collect the coal using the wooden pickaxe. So we'll do that intervention and save it in our SIG, and we'll say that the acquired coal sub goal is complete. So this example is complete. The environments that I did my experiments on are as follows. So I did experiments on Montezuma's Revenge because it's a sparse reward Atari game. I did another game which is Minecraft, which is hierarchical long horizon tasks, just like Montezuma's Revenge, but this one is um, more easier to control uh, and learn on. Procedurally generated coin run is the next example, where this is procedurally generated. It has sparse rewards and it has a shallow hierarchy compared to Minecraft, which has a deep hierarchy. Okay. Then we have Causal World, which has decent early shallow hierarchy, and it is a robotic simulation example where we can modify the stuff on the robotics table. Um, the next example is Cartpole, where we have continuous control. It's a classic example, and it has dense rewards, which is not suitable for my system. So the metrics I tracked are normalized return, the frames taken to get to 75% of the final return. I calculated the intervention of the precisions. The precision of the interventions. Uh, I also did track the option success, and then I also tracked the structural Hamming distance from the ground truth for my graph, causal graph. So in the right side, you can see my agent playing the game. It's trying to uh, get to the second level after grabbing the key, but it's not able to do that. And then it learns how to use the ladder, so now it can manipulate itself up and down. It also learns that jumping 2 floors at once is going to kill you, hitting an enemy is going to kill you, grabbing a key is going to give you a positive reward, and using a key with the door there makes the door open. So all of that has been learned, and it's able to clear that one room, and so it's able to learn these things and reuse them to complete the whole game as well. So with this, we have a pretty high normalized return using uh, causal curiosity. We also have a higher return for our system and CDHRL, which are almost tied at most points. At some points, because CDHRL is doing better because of the hierarchical depth that they have. Um, but at a lot of points, my system is also doing pretty good compared to that. So we are competitive with this um, causality driven hierarchical reinforcement learning for this example. Then we also tested on Coinrun, procedurally generated, like we talked about. Uh, the traditional RL agents do badly on this, but comparing those to our causal RL, we can clearly see that causal RL gives you a pretty big advantage for generalization tasks. Uh, the hierarchy here is shallow, so my system is able to use both the information that it learned in the probabilistic causal graph and see and the skill intervention graph, and is able to overcome all of the other methods that we tested against. Our intervention precision is also very high. That means that the interventions that we are doing, we are actually changing the environment variables that we intended to change more often than not. And this graph shows that it keeps increasing with time. Then our results on causal world are as follows. So our agent is performing very good against all of the other baselines. So one causal RL baseline was causal curiosity, and then we ran the traditional RL baselines, which were pretty much mostly failing. Um, and then on the right side, we can see an example where we trained on pick and place task with the try finger, and you're supposed to place it on the green place. And then in the testing environment, you can add barriers so that your distribution shifts, and a lot of your trajectories are no longer valid. So using that, we are able to figure out figure out that system using DIA. We also tried testing with block with less mass and less size than the one we trained on, and it does a decent job, but it fails a lot as well. Uh, so the contributions. Wrapping up. The theory contributions that I have done are create a formal link between causal inference, Bayesian rationality, and reinforcement learning, along with intrinsic motivation for curiosity. So that's that. We did a design of the PCG and SIG system for our discover, interview, and adapt system. Um, and then we interleave the loop uh, between those terms. All right. And then we also learned algorithms for variational PCG learning. We formulated a novel SIG implementation, and subgoal and information gain aware selector was formulated. We also have evidence across different domains with different ablations that show that interleaving and information gain are load bearing. Let's go back to our research questions, where we asked one question about the discovery. The answer is yes, that my agent has learned causal models online and using the agent's own interventions and used the plans that were learned for planning. So the answer is yes. The second question was about interventions, and we have a high option success rate and intervention precision, which prove that an answer would be yes. And we also have information gain, which reduces the PCG's entropy over time. So both of those things are working. Next question was about adaptability. So I think to a meaningful extent we have shown that we are able to generalize. But I also want to test this on higher states, higher uh, size of uh, state spaces, which it generally fails on. Um, and also, we say that this is interpretable to a great extent, but we need to do human studies on that to actually see if it does explain behavior. The conclusions that I have are causal structure helps. So even at matched returns, the system that I created, it is able to produce calibrated beliefs. We are able to get interpretable skills and also able to get a faster uncertainty reduction than other methods. Uh, so it shines in sparse reward, long horizon object centric tasks, and it's less useful for dense, tightly coupled dynamics tasks. And then we proved our design principle that interleaving and information gain is better than decoupled discovery or novelty bonuses alone. So let's go to the questions now. Um, I'm happy to take any questions now.